to COVID, we weren't able to use basically any of that. And they kindly agreed to extend the funding for 1 year, and we thought that it would be a great thing to organize a conference. And just, it's a sort of an informal event in a sense, so feel free to just ask questions, and it's for you to, meet everyone and, just have a good math conversation if possible. And there are just a couple of technical things. If EDU-ROM doesn't work for you, there is a Wi-Fi password there if you need. And there is dinner tonight. You're welcome to join. Please let us know maybe by the coffee break later if any of you want to join. We sent an email to some of you, but it's not a problem. And that's it. Yeah. I think. Oh, we'll have to just take your lunch preferences at some point
if you want
later. So we'll pass out the paper with choices and the next text for what you want. Okay. Other than this, I think we're ready to start. Okay. So our first speaker is actually the director of the Institute Geneve, Roberto Natalini, and he will tell us about mean field models. I don't remember
the title.
Yeah. On the top of my head. It's informal, so.
Yeah. So informal that you don't remember.
Maybe it's a multi-scale approach to cell movement.
Okay, so thank you very much for this invitation in my institute. It's a pleasure. No, but no, really, maybe the first time I give a lecture in my institute in my life. So that's so. I don't know with geophysical flows. I'm not going to speak about geophysical flows because I don't know nothing about that. So my talk will be more about biological flows and the movement of cells and cell aggregations. So there's a working collaboration, a lot of people. Just I mentioned a few of them. Gabriele Bretti, Thierry Paul, and Marta Menci, and there are some contribution from Tommaso Tenna, my former master degree student now in Nice, in France. Okay, so my motivations are from organs on chip, which are a technology recently developed to study cell movement, and in particular new drugs used for humans. And the idea is to reconstruct in a chip different organs, so to allow to small community of cells to reproduce, I don't know, liver, pancreas, lungs, and so on, and to try to look at, I don't know, you create a tumor in a pancreas, and then you allow to immune cells to respond to the chemical signals from tumor cells, and so also under the effect of drugs by knockout cells or wild type cells and so on. So you can try to understand what happens in these cases. And this is the structure. So you have usually some chambers where you can put cells and some channels communicating, which are more or less the functions of membranes in our body. And you try to have a setting more realistic than the standard Petri dishes used before, and much better than animals, because in animals you cannot look at the movement of cells. So what you have usually is that you subministrate the drug and you kill the animal and you look what happens, but you don't see what happens inside of the animal. So that's a recent technology. 10 years ago, the first experiments, and in general, this microfluidics is a large now sector in this kind of field, and there are a lot of projects. My institute now is a participant to a large Italian project, D3 for Health, 25 millions of euros to investigate this kind of digital twins of biological activity. But okay, so the final goal of this kind of models is just to look what happens from the microscopic level. I don't know, DNA, RNA, and so on, the internal of the cell, and so to scale up to the human body. And at each level, you need models to understand, and also the transition from one level to the other level. So that's crucial in this kind of problems to understand how to scale up your model. Because, okay, maybe you can model what happens in these organs on chip, but then the clinician come and they say, okay, you have a good model for 10,000, 100,000 cells, but I'm interested in billion cells because I'm interested in a liver, in a lung, not just in a small community. So how this model scale up to describe the behavior of organs. So that's a challenge. I'm not going to give you the solution today because that's a large programs. A lot of people are doing that. There are a lot of phenomenological models at the microscopic level, but they don't match with the microscopic one. So the aim of this study is to understand how to pass from the micro models to the macro models. Okay, so what I see, and I will speak about one experiment, which is I have a large chip, and I just this shot, that's a screenshot of a special part of this chip, which is just two chambers with some channels communicating between the chambers. On one side, we have tumor cells, this large one, and on the other side, we have the immune cells. And so, in general, here, red are immune cells, green are tumor cells, and they start chemical signals from tumor cell to immune cells move to reach the cancer cells. So what we want to describe this kind of phenomenon. And there are a lot of experiments. I refer to colleagues in CNR, for instance, this paper by Vachelli, but in particular, Businaro, the Businaro group in CNR, did a lot of experiments in recent years. And what they can look is to trace the trajectories of the cells, and they can look at the difference. For instance, when you have the knockout of the cells, so you have no chemical signaling, and so the cells have a chaotic behavior, as here, for instance, and or you have that these cells are driven by the chemical signals, so they reach their target. So that's a huge difference. But the problem here, you can acquire a lot of data, but you cannot detect the amount of chemical signal. You can just measure the trajectories. In fact, the position at each frame, and you have, one frame for minutes, from 2 minutes and so on. You cannot have a continuous movie, I don't know, like normal movies. So you just see some instantaneous of the movement of the cells. You can detect the trajectory and so the speed of the cells, but you have no information about chemical signal. And so here we have a movie, and that's our movie. In this movie, we can see what happened when you have this small one are here are the immune cells, and on this side here you have the cancer cells, the biggest one. And so since you have the concentration on the bottom on the left, so you have this trajectory, this slope, 45 degrees. Okay, that's our experiments. So the size of this screenshot is 1,000. The width of this is 1,700 microns, and you have 48, 72 hours, no more than that. That's difficult to do this kind of experience because each time you have a different setting, and so the problem in modeling is to understand why we have to model, and the answer is that you can do 3, 4, 10 experiments in months, but you can do I don't know 10,000 simulation in the same time. So that's easy to optimize, for instance, the chip, or to understand what happens if you move the cells, or if you have a different amount of cells just by simulation. So simulation is important, and also to design new chips in the future. And so the first model is naive, very naive. It's just to use the classical Keller-Segal model, which is a system of reaction diffusion equations, reaction convection diffusion equation, which are, you have an equation for one equation for tumor cells, and tumor cells are just diffusing, and they die. They die for many reasons, by natural end of life, which is not very high. Usually they are immortal, and also for the influence of immune cells. So it's a factor driven by a chemical component released by immune cells. So the movement of macrophages, so immune cells, they diffuse in this simple model, and they are driven by a chemoattractant given by the a phi is missing, okay? Gradient phi, a gradient field produced by the tumor cells, so there's the signaling. Then, and they can die with some, sometimes they can also die for some other reasons, for instance, the end of their life.
What is that? The legends of M?
Yeah, that's, I forgot phi, gradient phi. Yeah. And so that's to point out. Yeah,
it is non-linear.
it is non-linear because you have coupling. Yeah, and so that's quite classical. Keller-Segal, but it's a bit different from standard Keller-Segal, where the signal is produced by the cell themselves. Here, the signal is produced by another family. So you have two families. It's more like not Cavolterra model in some sense, because we have interaction of two populations. But here, the dynamics is very simple. Some years ago, for instance, I studied what's the name? The tuberculosis. In the tuberculosis, you have a really competition pre-predator model between bacteria and immune cells, because you are really a sort of a pre-predator interaction. Here is a bit different because in some sense, there is not that the immune cells are feeding themselves by eating tumor cells. It's a bit different. Sometimes they are not eating at all. They produce the release chemical enzyme, which is here, which is just produced by immune cells, and which is responsible for the death or inactivity of tumor cells anyway. So the system is quite simple. The difficulty here is more computational, in the sense that you have to connect the two chambers, and so because at the level of geometry it's quite difficult to construct this kind of numerical domain. We simulated that the two chambers are two-dimensional, but the channels are just one-dimensional. So we have the change of dimension in the numerical scheme. So we have to adapt the scheme, but it is since you have a lot of channels, it is cheaper than simulating all the channels like 2D. Also because the size of one channel is just one cell, and so adopt a continuous model to reproduce something which is at the same scale of the individual cells is not fair, I think. So you simulate the like one-dimensional, and
So, this one, if you go back to the model 1 second, in the equation for phi,
yeah,
instead of t, you have m.
no, for phi you have that the t is producing phi.
Yeah. No, but if you just, I'm saying, if you add m, then the two equations of m and t are
Yeah,
exactly the Galois-Segal.
yeah.
Right?
Exactly.
The parabolic,
Yeah,
parabolic.
yeah.
Okay.
Yeah, correct. Yeah, we started from this model.
Okay.
All right. And but anyway, so we produced a lot of simulation. I skipped the details of crank needles and so on, the numerical schemes. But the main problem was really this to connect to have this different dimension in the different domains. So you have to use some relation to bridge the cell to pass from one chamber to the other. And okay, so you can simulate and get something like that. Okay, there's a problem. First of all, our data are discrete because you are just the position of the cells. How to compare discrete objects with a continuous density? It's a challenge anyway. There are a lot of solutions. You can take an average of the grid and so on, but if you take just you take a grid and you take the number, you count the number of cells and you assign the value to this cell of the density, the problem is that very sensitive to the change of grid. So a better solution is to use a kernel density. So you imagine that there is a Gaussian with some, standard deviation, which is the scale of the radius of the cell on each cell, and you replace your population of cells with the kernel density. So you replace a finite number of points with the density, and you can compare what happens at this continuous level. And so after a calibration problem where you have some standard needles to try to compare, you can try to find a solution which is similar to the movement of cells. Okay, that's the result we obtained with the PhD thesis by Elisha Brown, and I was the advisor with the availability of this thesis some few years ago. And then when you want to show to biologists, to biophysicists, this kind of model, you come back to particles. So what you do is you sample your final density, you compare with the initial one. So here you have on the left, we have the red are the immune cells and the blue are the cancer cells. And on the left, you have the reality. On the right, you have the simulation. Okay, that's fine. That's not so bad because you have a lot of approximations. We don't know nothing about the chemical signaling, but it's not enough. We have a 20% of error anyway. It is a lot. I'm not satisfied with that, and the reason is the fact that it's difficult to take into account the single interaction of the cells because the movement of the cells is described just by diffusion. I mean, also by the gradient field produced by the chemistry. But the main point is that the movement of the cells now, we know, is not just diffusion. Because diffusion means that you are a cell, you see that there is some space in front of you, you go in this direction, okay? That's a Fick law. The Fick law is just, okay, I go where there is a lower density, nothing else. So, it's a very simple mechanism, which is quite different from the real mechanism of the cell interaction. So we started to try new models, and in this direction, we tried what is the Newton equation for the cells. Hybrid models. The hybrid models, which are discrete and continuous, So you take some few cells, tumor, you take a smaller region, and then you look at the individual cells, and each cell is moved by a ordinary differential equation, and the chemistry is still described by a diffusion equation. At this level, the diffusion equation for chemistry is good. In there you have molecules, so I mean, you can assume that the diffusion is fine. And so we for the paper, other recent papers, the idea here, we introduce some stochasticity inside of the model, some Brownian motion, and so you write an equation, which is the Newton equation for the cells. So you describe the forces acting on the cells. And the idea is that you have few terms. And we introduced this kind of models with Luigi Preziosi some years ago, 10 years ago, to describe the movement of morphogenesis in the zebrafish, and that's what we try to use also for this problem. So we have chemotaxis term, so the force is given by the chemical film. You have some interaction between immune cells and tumor cells, which are maybe attraction repulsion, other standard terms which are usual in this kind of problem of individual-based models. And you have also terms due to the attraction repulsion between immune cells themselves or alignment, other terms. And here we have also the damping due to the interaction with the substrate. And also this velocity is perturbed in a stochastic way by Brownian motion. And the equation for the chemistry is the same. So this is a sort of Keller-Segal model at the discrete level also. And we produce some trajectories which are, I mean, quite similar. You see that the red one are produced by this model. The standard ordinary differential equation is the blue one, and the experimental is the black one. Probably Levy flights would be more adapted to this one, but to simplify anyway, the model we just state on just Brownian motion. And okay, so that's the modeling. Now the idea is how to scale up from this model to come back to the microscopic environment. Okay, now I study a sort of a toy model where I condense all the forces in this term, which is just given by just a single type of force, which is invariant by translation and change of coordinates. So you have just the difference of speed and the difference of position. And that's similar to Cooker's main models for individual basic model for the flight of birds. And still, this model is coupled with chemotactic. So it's a sort of simplified model. I just restrain my analysis to one family. It's not difficult to differentiate the family, but just now to focus on one family. So this is really the analogous of Keller-Segal, because that's the inference of the production is given by this cell. So that's different from the previous model, just to simplify the mathematics environment. And at the level of simulation is the same. And so we want to study how to pass from this model to the microscopic one. And there are a lot of results without chemistry. The Cooker-Smale model was well studied. It was introduced by Cooker-Smale in 2007. Then there are some results by Ha and Liu, a lot of results from Carrillo, I didn't mention here. And anyway, what is the main result in this problem of aggregation is you have the confinement. So the speed tends to be the same in long term. and also the individuals stay in a compact set after a while. And so there are a lot of study. There is a flow. This flow is given by the ordinary differential equation. You have a Liouville equation, so you can extract a flow from this equation, and there is a first mean field approach to this kind of problems, which was proposed by Ha and Tadmor in 2009, and the idea is to make an empirical measure, so to put in each corner of a grid a Dirac mass, and so to tend to the limit to this in the Wasserstein distance, and to approach the solution of the Vlasov equation. The Vlasov equation, you can deduce the Vlasov equation from the Liouville equation formally. It was deduced in the first paper by Tadmor. And then there are a lot of results. There is a good review of all these results by Carrillo, Choi, and Jungpil, quite recent, in 2021. And so you have this Vlasov equation where the forces are described by a non-local term. So inside of the Vlasov equation, you have an integral taking into account the microscopic forces. So you have a new equation. And so there is a theorem. You take an approximation of the empirical measure. You take the initial data, and you assume that the distance between the initial data for the empirical measure and the initial density in the Wasserstein distance goes to zero when the number of the individuals goes to infinity. And in the limit, you find that the limit is the unique solution of the Vlasov equation. You can show that there is a unique solution for this equation. And the solution is an infinity with values and probability. And the lim sup of, when n goes to infinity, of the supremum on all time of the distance between the solution, the empirical measure is coincide with the solution of the ordinary differential equation, goes to the solution of the Vlasov when n goes to infinity. And the last result is quite strong because you have a uniform bound for all times. Okay, that's what we found with Thierry Paul when we studied this problem. So we started without chemistry at the beginning because we wanted to understand the problem in a simple setting when you have a Liouville equation. So again, the idea was not to consider empirical measure, but to use marginals. Marginal for people dealing with kinetic problems are more natural because what you are looking for is you average all the other particles, you see the individual particle, what's the probability density for one particle. Okay, so that's the standard assumptions to build up, I don't know, Boltzmann equation and so on. So it's more natural, this setting. And so also at the level of initial data, I find a lot of quite artificial the fact that you take a grid and you put empirical measure on the corner of the grid. Here you start with your initial data. Clearly, these particles are indistinguishable, so we have some assumption that they are independent, that you can replace one particle with the others. But for immune cells, for instance, it's quite natural to take this kind of assumption. And so the problem is that here, again, you can construct a flow, and from this flow, you have, in a natural way, the Liouville equation for the problem. So you start with this flow, and you introduce the first marginal. So you integrate all the other variables, and you have just a density function, which depends only on x and c. So it is on the same dimension of the solution of Vlasov equation, because the Liouville equation is in a bigger space because you have n particles. You are in 2 n plus 1 dimension. Here, okay. Carica la batteria. No, bisogna prendere la mia cosa che sta nello zaino, che sta nella mia stanza. Eh? Sotto la mia scrivania, pensavo che ce la facesse, invece non ne voleva sapere. Però vedi, questo qua rimane perché è caricato lì sopra.
Ma il pointer ho detto. Il pointer
No, no, perché io sto proiettando su, I'm sorry, in English. I'm using 2 computers, one for the streaming, one for the presentation. So I have to wait. Anyway, sorry. I assumed my battery was too powerful. Hmm? Yeah.
So in the continuum model,
Yeah.
so the interaction, so there is no specific interaction with the channel for the field representing the macrophage density.
Yeah.
It's just a because you have this array of channels, right?
Yeah.
It's just
Okay.
a no flux condition.
No. It's okay. Where you have the channel is one dimensional. I assume it's one dimensional because, in fact, in the reality, the cell is, I don't know, 10 microns, something like that. And the channel is more or less the same size. Even the cell has to squeeze a bit to enter this.
Because there is where it's the granularity of the
and so we have a relation to pass from the chamber, which is 2D. There's a way, and that's dimensional reduction. So it's interesting because you are on the computational level. If you want to have a grid at the level of the channels, you have to have submicronic grid. Yeah, you have a transmission condition, which is between the chamber and the 1D, and so you are reducing the 1D so to grazie. You are reducing the 1D to the 2D. I mean, you allow this one. It's quite standard. There are a lot of works, but here we do more. I skip this part, so thanks for the question. Because the main point in this story is the fact that on the channels we use an hyperbolic model, just a sort of wave equation. Because in this case, the transport effect is much more important. In fact, the dynamics is different because here you have a sort of I mean, you are not no more swimming inside of the liquid. You are gramping inside of the channel, and so you have to calibrate the constant, the speed inside the channel is different from the speed that you just the diffuse speed that you are assuming outside. So I mean that's okay. A special case, in a special trick, we tried also to use a parabolic model inside. The hyperbolic is much better and much more respectful of the reality of the simulation. Now, I hope that is okay. Okay. I enter. Because we have a problem here, the fact that, okay, I can do another thing. Okay. I can do that. I don't know if it's okay. I hope that it is seen online on YouTube. Okay. Sorry. Okay. We were here. Sorry. And so the okay. Okay, when you pass on this formulation on marginals, it is possible to use Wassestein distance to prove the convergence of this density to the solution of the same Glashof equation. So the result is different. It's different in this regards that here, what you obtain is we are dealing with the Wassestein 2, so the Wassestein L2 measure, and we have one positive results and one negative results. The positive results is the fact that we can estimate the error. So we know from these estimates that the speed of convergence is like 1 over square root of capital N. N is the number of particles. So this estimates was not produced by the technique used for the empirical measure. So that's one advantage of this approach. The disadvantage of this approach is the fact that here we have an estimate in time which grows exponentially in time. So we have not a uniform bound, and that's impossible probably with this technique to find this kind of bound. So we know that for reasonable time it is okay. Anyway, in the life it is not time going to infinity, because anyway the time is finite, unfortunately, for the cells. So maybe we can be happy with this approach. But anyway, because anyway the constant you have the bound you have with the empirical measure is unknown, so you know nothing is 1 billion, you don't know. And but we have a precise estimates of all the terms of the constants in terms of the initial data. And here I'd like to focus on the tool we are using. This tool is not completely unknown, but in this formulation is the first time we found this kind of statement. In fact, it is possible to compare Vlasov problems. So if you write a problem in a Vlasov form with integral terms, and which depends not only non-local in space, but even non-local in time. And so that's the main point. When you have terms which are this kind of characteristics with some Lipschitzianity you have to assume. So it's possible to have this kind of ground wall lemma for the problem. So you have two different speeds. You have V1 and V2. You here, you have that this distance is bounded by the initial data with this growth, exponential growing time. And you have the difference of the two fields. So you have V1 and V2, which depends non-locally in time and space from the whole problem. And so we have the difference of these two fields in a sort of the difference in L2. And so this term is the main lemma we are going to use. And it was not completely obvious, but that's the main tool also for the work when we attack the problem of chemotaxis. But here, the idea and the main lemma is that, first of all, that when you want to compare two measures.
Yeah, sorry. Yeah, V1 and V2 are given.
Huh?
V1 and V2 are given.
Yeah, yeah. In this setting, they are given. Yeah, yeah, yeah. And that's the main point, because then clearly we want to have the terms with depends nonlinear in the solution, and so you have to close some estimates. Okay, but the main point is to have the equivalent of ground wall lemma when you do some fixed point techniques, I don't know, for energy estimates and so on. So there's the equivalent for the vast system. But the way you obtain this is completely different, because here we have to deal with couplings. And the couplings are, I mean, you cannot just take the difference of the two measures. Okay, but you have to construct the couplings encompassing the two measures. And so we have a double flow. You double the flow of your equation. So here you take two measures and you construct the double equation. You have the double number of variables, and you compare by this lemma, which is more or less written in some paper by Gauss, Paul, and Moore. But here we reprove it in this setting, which is quite different because they introduce this kind of techniques for quantum mechanics, essentially. And so you introduce this sort of energy, which is equivalent more or less to the distance, to the vast system distance, and you obtain this inequality. And you see that from this inequality, you have clearly this difference in L2 of the two velocity fields. And so you can obtain this, they are like big characteristics microwave analysis in some sense. So instead of constructing the difference between the two functions, you double the number of variables and you look at the total flow, which is couplings between these two measures, because the standard way to attack the problem of vast system distance is to prove that there is a coupling connecting the two measures, and so looking at what happens when you minimize between all the possible couplings between these two measures. So that's really at the core of the definition of vast system distance. And it works in the sense that also numerically it's possible to look at they are quite similar, the behavior of the microscopic model, so without chemotaxis and density. So here you have the cell moving, here you have the velocity, and here you have density. And the problem is that you have floating, so velocity will be the same in the end. And so they are aligning from v equal to 0, but they are in a compact set in X. And okay, also in the case where there is no floating for large values of one special parameter in made, you obtain the same result. So I mean, there's a good correspondence between Vlasov equation and the discrete equation. What happens when we introduce chemistry? And when you introduce chemistry, it's much more difficult problem, because there is no longer a flow, because it is non-local. The heat equation is not reversible in time. So you cannot have an Hamiltonian flow, and you have another a Liouville equation. Yeah. So really, we are in different setting, different framework. So we spent almost the first result was quite easy to be obtained. We worked some months here during the stay by Thierry Paul, and we spent 1 year to find this second result, because we were starting from the fact that it was even difficult to write the right equation. And then, but you can still write the Vlasov equation. I mean, you have a target, but you have to pass from the discrete model to the kinetic model in some way. So the idea of this proof is to construct the approximation, coming back to the empirical measure, and okay, that's the result. But I don't want to enter in details of the proof. But the first proof is, first of all, you introduce an empirical measure. You introduce an empirical measure, I mean, you replace the Dirac masses on the original equation. This equation satisfies a Liouville equation, but just for empirical measure. So you show that you can pass from the general problem to this problem in, with the stability theorem. So the previous stability theorem applies to this new problem, the previous lemma, and then from this problem of pseudo-Liouville equation converges to the Vlasov, again by the marginals. And so the result is the same, more or less, because here is much more technical. Here we have an estimate in all dimension with some n to the power minus 1/2 log n and so on. But the main point is how we obtain the conversions of the chemical gradients, because this one is much more delicate, because each time the chemical gradient is connected with this specific solution. I mean, you start with initial data, you construct the solution, and you have just one field given by this solution. And so here the measure you are introducing is, okay, the density of the initial data, but also the initial position and velocity of the particles at the initial time. So that's the measurement you are using, not any measure, not the back measure or anything else. You are weighting this distance by using the initial position. So it's dependent on the initial position of the particles. So it's quite difficult results, and we spent a lot of time to understand that it was the only possible results we could obtain by this technique. Okay, and it works also in this case because the situation made by Marta Menci. Again, here we have chemistry, and the difference when you have chemotaxis is that you are collecting the particles around the center of mass of the particles, because you have also some forces. Here we have no damping in this simulation, so but you have just alignment given by Kuckel's and these attraction forces. So it is, you are squeezing the particles in the same place. If you neglect the alignment, you have an infinite movement, because you have a forces, so your inertia, and they start to oscillate around the center of mass. Here, with the alignment of plus chemotaxis, you obtain this result. And okay, this one, it was in the old non-flocking case, and still you are in the non-flocking case, you have the fact that you have flocking because you have a chemotaxis. So even in the case where without chemotaxis, so you have no flocking, here you obtain the same, and that's consistent with the macroscopic case. Okay. Now the problem is to pass to the final step, hydrodynamics. So in the hydrodynamics, the standard results obtained in recent years from Vlasov in particular with this kind of Vlasov with non-local terms, I just say one word on the fact that here we are using non-local in time and space. So the history of the problem is important. In the previous result by Carrillo, also Figali, attacking this problem, they use it just sometimes non-local, but just in space. So the technique is a bit different at the level of proof of the theorem. But anyway, one standard way is once you have a Vlasov, you can treat the monokinetic case. Monokinetic case is the fact that you take a density, which is the initial data for the density is given by a density space and the Dirac masses for the velocity concentrated on a given field, okay, on a given field on X. And so it's possible to prove, but this is not a big theorem, it's a standard. I mean, that if you have a solution for this Euler non-local problem with no pressure here, we are in the monokinetic case. So, I mean, we have not the second momenta of the problem. We have zero in this case because we are just dealing with the specific initial data. And here, so we have this non-local problem with chemotaxis. So we have the full problem if we have a solution of this modified Euler problem, which is regular enough. So until the solution exists, if you take the density given by the density of the Euler Dirac on the solution on the field U produced by this Euler equation, this one is an exact solution of the Vlasov. So you have a perfect correspondence between the two problems in this specific case. Okay, and so it's good, not very good, because the problem is that in general you are not monokinetic, and if you are monokinetic at the beginning, you lose this property in time. So the fact that it is for short time you can prove that you have existence of this fact, but for large time is impossible. But for many reasons. First of all, you have an hyperbolic problem, so you can have shocks in principle. But even if you have no shocks, the velocity is no more concentrated on a Dirac mass. So that's in general you are spreading away, and that's possible just numerically to see this one. Okay. So we want to compare what happens from the non-local Vlasov and our non-local hydrodynamic, the Euler non-hydrodynamic. So you take the first two moments of the Vlasov, you compare these two first moments with the solution of the Euler. And if you are monokinetic, it works. So you take a very special Gaussian monokinetic solution. And here is the solution in Vlasov space. Here, no chemotaxis, no damping, very simple situation. And we have a good approximation. But if you again, with the monokinetic case, the different initial data, after sometimes for t equal 2, again, no damping, but here there is chemotaxis. You have this one, which is no more monokinetic because we have more values for the same x. And so here you are losing. Here it's not clear, but for instance here is quite different. The solution, first momentum of the solution with compared to the solution of the Euler. And so if we add damping and chemotaxis, you can reduce this effect when you are monokinetic, because you are anyway dissipating energy. Why you are losing the monokinetic case? Because the second momentum is energy, is temperature. So when you have a very large energy at the beginning, this energy cannot be neglected in the future, so you lose this monokineticity. And but when you are far from the monoclinic case, clearly you have a completely different situation. So here, for general initial data, there is no convergence or convergence for large times when you have chemotaxis, no damping, because there is no reason that the energy stay small or can be neglected. So, but our main goal, which is not achieved anyway, is to understand what's a good macroscopic model for this kind of problem. Because anyway, we want to pass from this hybrid equation to the macroscopic model. Vlasov is impossible to be used, for instance, in 3 dimension. In a simulation, is almost impossible at the level of computational. Also, to look at what happens under this. We are not interested on the single behavior of the velocity of the particle, so we want to compute hydrodynamics. So we compare with this model with another model, which is quite well known and used in particular in vasculogenesis and androgenesis, which is the Preziosi model for chemotaxis, which is a bit more realistic than the classical Keller signal. And this model is an Euler model coupled with the chemotaxis equation in some nonlinear pressure. So the idea is to replace the second momentum, which are neglected in our reconstruction, with a small pressure. So taking inspiration from this model, and what happens? Okay, it happens that if you have chemotaxis and no damping, we are quite far from, even for a small pressure, we have to mimic the second momentum. But for with damping, we recover here for some value of epsilon, we can recover a realistic situation where in this case we know that the velocity is zero for large times, and then we can recover this kind of problem. So as a phenomenological model is not so bad. I just finished with the comparison in 2D because all these comparisons were in 1D with the master students at Mathgeo. We did this kind of simulation recently, just comparing from the initial data we reconstructed by kernel density the situation for the model we developed with Thierry Paul without pressure and the Preziosi model. And anyway, this pressure is in some sense diffusing too much with respect to the real position of the particle. So to keep this kind of non-local interaction, maybe working more on the structure. For instance, here we have an alignment model. We can work more on the attraction, repulsion, and so on. Maybe this model is more realistic anyway, even neglecting this pressure term, than the Preziosi model, which is finally for large time to diffuse it to have a realistic description of the position of the cells. Sorry for the inconvenience during the talk. I could pass immediately from one to the other, but I forgot I have the presentation also on this computer. And so here a short list of references about this work. Thank you very much for your attention. 3 minutes later. 3 minutes later.
All right, thank you very much, Roberto, for your talk. Any questions, Greg?
Sure. So at what level can you compare between data and models? I mean, can you do this at the level?
Okay. Yeah, you're right. So that's the problem. In fact, this master thesis we did was just to understand this point. At the first level, you can compare the microscopic model, the hybrid model, with data. But it's not easy, because if you do that, you have to, you have positional particles. So in principle, you have a finite number of points, and maybe you can reconstruct the speed by using the different position at 2 different times. But you have a finite number of trajectories. If you want to do a simulation in a place where you have no data, and that's a lot of place because you have no data in general, you are in trouble. So one way, and what we did in our work, I skipped this part, but anyway, the way is to reconstruct an interpolant surface of the speed, the space of speed. So even where you have no data, you have a credible data in this case. But quite dirty as a technique. Much better to pass to the density. So to translate your results by current density technique to density results and to compare Vlasov or macroscopic models with the data. And in this case, you have a lot of technique of comparison of data. You have to minimize the functional in a large space of parameter in a way. So that's, you are more, I mean, it's difficult at the computational level, but not impossible. And our experience was that you have a good calibration, 10%, 5% of error in some cases. So in one dimension, in two dimension, you increase. So the introduction of these non-local terms, which is the real novelty finally, to introduce this local term, which takes into account the microscopic interaction, even at the macroscopic level, is important. And to maybe you can calibrate a part of this parameter for the non-local terms at the microscopic level, and then to use the macroscopic level to calibrate the other parameters. Anyway, that's a problem. It's not easy. Also because the data, we are not in a big data situation. We are in a small data situation because when you have 2, 3, 4 experiments with 10,000 cells for, I don't know, 2 days is the maximum you can obtain from biology. So you cannot expect to have billions of data. You need in part for calibrate this kind of models.
Okay, maybe I don't know my question, but so you said that let's say the loss in time is exponential.
Yeah.
I was just wondering because usually people in quantum mechanics they get the double exponential.
Yeah.
And I don't know if you can comment about it. I mean, gain is.
I don't know quantum mechanics, so I cannot comment this statement. But in our case, this single exponential comes from the fact that anyway, you have just it comes from just the initial data, because when you have the first, also from the difference of speeds, but even if you skip the part of the speeds, even for the initial data, you have just this single exponential. In the speed, you have just one integral from 0 to t. I mean, in this model, we have just one exponential.
When you do, yes, okay, essentially double exponential
comes from
the fact that you make 2 times Gromval. So you do an energy estimate for log of something and then you iterate it.
Okay.
So that's, but okay.
Here you directly work just with one density. Yeah. Okay. So I mean, probably is this one.
From Blasov equation, you don't expect that there is a rescaling of parameters that which gives you this monokinetic regime. So for short times, maybe.
Yeah.
To rescale everything, and maybe there is a small parameter problem.
Yeah. Okay. I don't think so, because I mean you can take your initial data monokinetic. Okay.
Yeah, I'll come back.
Yeah. And so you have a short time existence, but the problem is that thanks to the cells, there is no reason that the position of the cells determine the speed the cells have in the future. Because the speed of the cells in this point, because when you are monokinetic, it means that if you are in a point x, your speed corresponds to ux. Okay, so it depends only on the position. But for a cell, there is no reason you have this kind of behavior. Usually, that's your history, the signal at that time, and so on. So it depends maybe on other factors. In fact, once you introduce chemotaxis, immediately you lose monokineticity even for short time t equal to, which is normalized. You lose this
diffusion part on 5.
Yeah. Yeah, because I mean it depends also on this one, also on 5. So I mean you are mixing, but even for Kuckersmell, you don't expect in general that even after rescaling the particle in Kuckersmell depends on the position of the other cells. So not on your position. So, I mean, it's quite artificial. You can keep for some times, but not for all times. I think it's hopeless, but anyway, it's my impression.
Okay.
If I can ask one more question, please. So when you do the equation for the marginals and then you stop at the first marginal, could you?
Sorry, I didn't
So
understand.
when you derive the equation for the first marginal,
Yeah.
so this like we would say ky hierarchy, right? When you stop at the first term, would you consider?
Okay, now, good, a very good question. In general, in biology, you have no reason to understand what happens to the energy. I mean, it is not gas dynamics, this one. These particles have a lot of exchange of energy with the external. They have food, they take, I don't know, light, energy from other. There is no conservation laws for energy, no balance law for energy. We don't know. So, I mean, it's quite artificial to introduce another equation. For semiconductors, you can do that for other problems. But for my opinion, even for, I don't know, pedestrians, traffic flows, and so on. But when you have individuals, there's no balance law for energy. So, I mean, I don't know how to feed the equation for energy. What is the right hand side for this equation? So, I mean, it's quite complex.
Okay, maybe we can thank Dr. again. We have coffee and pastries over there, so we'll resume in about 20 minutes.
D'accord, d'accord.
Sì, sono ragazzi, una volta magari scriviamo che
Avevo potremmo anche votarsi, cioè includeva il giorno che c'è la cosa in cui
All right. So I think we can start again. Just a second. You're doing the and second speaker of this morning is how do you pronounce your last name? Actually? You should have asked the first day.
Bishop.
Archbishop.
Lucas. And Frank Panjani, tell us about fixed rate loans.
Thanks, Michele, for the invitation. It's a pleasure to be here. It's my first time in Rome, actually. So I will present you some recent results about the spray equations in this particular case of fixed spray. So it's mainly a joint joint results with Daniel Amquan, who is now director de recherche CNRS in Nantes, France. And then I will present maybe some extensions with also with Émeric Barada, who is the CNRS in Lyon. So I will present you what are these spray equations, mainly the general setting, and then this particular heat spray regime, which is really, the study of this regime is really at the beginning, and what I will present you is really a first result, which I think opens many, many questions. So I'm trying to convince you that there are many difficulties that may arise, and there are some questions which are really unsolved. So I would like to highlight this difficulty. So feel free to ask me if you have any questions. Okay, so a bit of motivations. So the general setting is the following. You try to describe the evolution of a cloud of particles which are evolving within a fluid. So it's a kind of two-phase problems. We have these particles, which can be, for instance, small droplets or dust specks, for instance, and they are evolving in an ambient gas. So it covers actually a lot of physical situations. For instance, in what I will describe for the thick spray regime, as you will see, it's relevant, for instance, for this kind of problem, geophysical problems such as sand flow in pipelines or this volcano aerosol that may arise in the atmosphere. So generally, this interaction, this suspension between particles and fluid, we call it a spray or aerosol. It's a very generic term. Okay? And it arises also in combustions, particles in the atmosphere for medical purposes, and also sedimentation. So you have many ways of describing such suspensions. For instance, you may try to describe each particle one by one, etc., by Newton's law, as you have seen formerly. But here, I will adopt what I call a fluid kinetic point of view. So it's, I build on kinetic ideas with now a fluid. So for the fluid part, I will adopt a macroscopic description, which is a standard, say. So I will describe the fluid thanks to Navier-Stokes or Euler equations with equation on the fluid velocity u of tx and the density of the fluid rho of tx. For the particles, I will adopt a kinetic point of view, which is a statistical mechanics point of view at the mesoscopic scale. So you have a lot of particles, and you will try to describe them thanks to, as you have seen, Vlasov equation or say Boltzmann equation. And your favorite object in kinetic theory is the distribution functions of the particles on the phase space, f of txv. So you have an additional variable, which is a velocity variable v. And f of txv dx dv, you have to think about this object as the number of particles at position x, which have velocity v at time t. And of course, what's at the macroscopic level, say, what makes sense is not the particular value, pointwise value of f. You're not really interested in this. You are interested in averages in velocity, at least, of f. So I define these two kinetic moments that we'll come back. Rho f, which is the average of f along just along v, which is the local density, and jf of tx, which is the first moment in velocity when you integrate against. So this is local density and the local current. So the fluid will interact with f through this quantity. So you have a lot of models which may couple these two phases. Here I will introduce a classification which has been settled by O'Rourke and Williams in the 80s for engines purposes. And the classification is based on the, at least formally, on this fluid volumic fraction that I call alpha. So alpha is 1 minus the local density of the particle, so 1 minus rho f of tx. So up to a normalization, it's the fluid volumic fraction. So say it's between 0 and 1. You can imagine this factor, okay? So it's for the fluid. And you have, say, two regimes. The first one, which is a thin spray regime, is when alpha is close to 1. So the fluid volumic fraction is close to 1. It means that the particles, the cloud of particles, is really dilute in the whole suspension. Okay, the fluid volumic fraction is close to 1. In that case, in the mathematical community, it's referred to as the Vlasov-Navier-Stokes system, usually. So it may differ in the engineers community, for instance, or physical one. In math, it's mainly, if you're interested in this, it's Vlasov-Navier-Stokes. Okay? So this kind of models, their variants, I should say now, since 20 years, it's kind of well known. You have, for instance, global weak solutions, à la Loré, for instance. You can study the large time behavior, which I think is very interesting. So you have this monokinetic behavior which appears for large time results. You have hydrodynamic limits. And now people are really focusing on the derivation of these equations from particles dynamics, which is even more complicated than the deriving Vlasov-Poisson. Because you have the balls in a fluid with which may interact and so on. So, but the picture is quite complete. But today, I'm interested in the other regime, say, the fixed spray regime, which is when alpha is not close to 1, which means that the cloud of particles is not so dilute compared to that of the fluid. So the fluid volumic fraction is not so small, it's not so big compared to that of the particles. So you have big cloud of particles, say, in the whole suspension. And for this regime, to my knowledge, the math are quite absent. Okay, nothing is known even at the first questions of existence of solutions. Actually. Okay, even though it's really used by engineers in CA in France, they know this by heart, but it's quite unclear what to do with this actually. So I will build on what's really in this model just after. But let me insist on the fact that this kind of regime is really connected to two-phase flow equations. Okay, when you have a gas and a liquid in the same suspension, non-miscible. And it's possible to link formally the fixed spray regime to these two-phase flow equations. And it's well known that these two-phase flow equations, they display some non-hyperbolicity regions. And because of that, the mathematical study is like a mess. Okay, so it's well known from the engineer community that this regime should be really hard, but they have this in mind, two-phase flow. So I will try to give and present you some first step in the study of this fixed spray regime. Okay, the main question actually, which is asked by Laurent Desvillettes since a lot of years, more than 20 years, is that is this fixed spray regime garbage? Should you use it or not? Knowing that it's related to kind of dreadful equations. So what are the equations? So don't be afraid. I'll try to explain a bit and emphasize the main point. So you have fluid equations and kinetic equations. So your unknown are F, rho, and U. So rho and U are density and velocity for the fluid, and F is the kinetic distribution. So in the fixed spray regime, you look at compressible fluid. So you have two equations, say one on rho and one on U. So it's mainly the conservation of mass, okay? So it's a continuity equation for the fluid, and then it's a balance of momentum for the fluid here, okay? Forget about alpha, for instance, take alpha equal to. If you don't know too much about compressible fluid, actually, don't worry about U. I will be mainly focused on rho, which is a continuity equation. And then I have the equation for the particles. So it's a Vlasov-Boltzmann type equation here. So you have the free transport of F at velocity V, and particles are also accelerated. And they are accelerated by the fluid around, with two forces, say. The first one is a drag term. Okay, the fluid is dragging the particles, and at least in some regime, we have this Stokes law that this drag is proportional to the relative velocity between fluid and velocity. Fluid velocity and particles velocity. So it's proportional to U minus V. So you have this minus V, which produces friction term. And you have another term, which is a pressure gradient from the fluid acting on the particles, because the cloud of particles is not dilute. So the particles feel the pressure gradient from the fluid acting on them. So you have this minus nabla p of rho acting here. And since the particles are quite big in some sense, you have also to take into account the collisions. So you have this maybe Boltzmann type operator, which may be really massive. Okay, I can consider nu equals 0 or nu equal 1 for Euler type or Navier-Stokes type. Okay, if you prefer. So here I just have a Laplacian. You can do more subtle one, but say this one. And you have a retraction from the particles on the fluid, because they are like by Newton's third law of this retraction. So what is this retraction? From this force, so for the first drag term u minus v, you will integrate this term and plug it into the right-hand side as a source term acting on the momentum. So with a minus sign, so you have this jf minus rho u with these two moments, and this term produces an alpha, okay, which is 1 minus rho. And one of the main features is that in your fluid equation here, it's not rho, it's alpha rho everywhere, because you only have one fraction of the density. So you have to multiply rho by alpha rho. So alpha was a fluid volumic fraction. Okay. So the coupling is through the drag term and the retraction, the pressure gradient. So in the barotropic case, because you are with a compressible fluid, P is not an unknown, it's given. It's a function only of the density. In a simple case, say we can think about a power law, okay, given by thermodynamics. And you have this volume fraction for the fluid, which is at some point here, and which gives you more nonlinearity. So this is the whole picture, which is a bit frightening, at least for me, at first sight. So you want to deal with this. And until now, it was really unclear that you can even construct solution for this. What you can say about this, nothing was known. So, okay, you can say okay, it's a nightmare, it's not really beautiful, but what are really the main difficulties, actually, okay? So, to simplify, I consider the case, sorry, nu equal 1, so it's Navier-Stokes. Okay, so imagine that u is better than the other ones, okay? By, say, parabolic estimates, u is better. So I don't care about u, okay? And I remove the collisions. Simply. And I just look at simple energy estimates to see what is happening. So I look at the equation on F. So it's a kinetic equation, but actually it's just a transport equation in the phase space. And I just rewrite this, splitting between this one and the contribution of the gradient of P rho. And I perform a standard Sobolev estimate. So since it's transport in the phase space, you will be able to estimate L derivative of F by at least L derivative of the force, but in the force you have an extra gradient. Okay, so you will pay one more derivative, so you will estimate at least F in HL by rho in HL plus 1. Okay, and then I do the same for rho. Okay, I looked at the equation on rho. So it's a bit maybe more complicated. It's not an equation on rho, it's a continuous equation on alpha rho. But alpha you can always replace by 1 minus rho f, okay? So I just rewrite the equation on rho like this. Look, here. I just developed everything. So you see, if you take f equals 0, which means alpha equal 1, you end up with a standard continuity equation on rho, as usual. Here, it's twisted by the alpha. So you have extra terms. Okay? Yeah. But now you can use energy estimate, perfect energy estimate, sorry. So you will estimate L derivative of rho by L derivative of the force, but you have an extra derivative. And in this force, you have moments of F, but in derivative in X, the moments in V, they don't see this derivative in X, so you will pay, at some point, L plus 1 derivative of F. Okay? So you can claim, okay, but it's not F, it's averages of F. So, you know, maybe averaging lemmas and so on, which gives you more regularity, but you may be able to regain at most 1/2 derivative, not a full one. So you have a loss of derivative. So I can estimate f by rho plus one derivative and rho by an extra derivative of f. And so in the end, I have a loss of one derivative on the unknown f rho. Okay, it's as if you are able to only estimate f rho by dx of f rho due to the coupling in transport equations. So usually with this kind of stuff, you cannot perform, except from the Cauchy-Kovalevsky scheme and analytical regularity, you cannot construct solutions in finite regularity because it's loss of derivative. You cannot perform a usual scheme, etc. But here you don't want to use analytic regularity for transport equation. Okay, you don't, because if you take compact support, you will be zero. So for kinetic theory, it's a bit maybe not what you want to do. Okay. But anyway, it has been conjectured, it was more a question for a program, it has been conjectured by Céline Baronger and Laurent de Villette that at least in the case nu equal 1, you may have some hope to do something, but it has to be done. Okay? And so we can imagine that for the case nu equals 0, you have also a loss of derivative coming from u. Okay, so it's even worse. Okay. So there is a little remark maybe that you may do, actually. If you come back to the equation, actually, if you consider now the unknown f, alpha rho, and u. If you do this, you see that actually you have no problem in the two first equations because it's just compressible Navier-Stokes on the unknown alpha rho and u. And actually, the loss of derivative is just coming from this term, okay, in the equation of f. Okay, so it kind of says that these estimates are a bit naive. So you have another way to see this, but there is still a loss of derivative. But actually, if you do this, so I won't present this, but if you do this, you are not able to treat like non-barotropic cases when you add the temperature. So the model is more involved, but with this technique, this point of view is useless. So I will stick to this one on f and rho. Okay. So, so when you have to start by something. So actually, we took our inspiration from another problem, which is coming from plasma physics. Actually. So it's about singular Vlasov equations coming from Vlasov-Poisson. So you will see the link in 1 minute. So on the left, you have the Vlasov-Poisson equations for ions in the backgrounds of fixed electrons. So you have this transport equation velocity v, and you have a force which is the gradient of a potential, and the potential is solving a Poisson equations, okay, Laplace equations, with the source term which is the local density. But for when you consider ions, you have this identity here, okay. And in physical regime, which may be of interest, actually you have an epsilon, which is the so-called Debye length in front of the Laplace. And this epsilon is really small, actually. So formally, if you take epsilon goes to 0, you remove the elliptic regularization given by the Laplacian, and you end up with this really simple equation. So still a transport equation. And now the force is just given by, now u is rho. Okay, so your force is the gradient of rho itself. Okay, so this model, which arises in the so-called quasi-neutral limit from Vlasov-Poisson to this one. This model has been coined by Claude Bardot's Vlasov-Benet equation, or Vlasov-Dirac-Benet, because it is as if Vlasov-Poisson was replaced, you replace the Newton kernel by Dirac mass. But you see here, you have no regularization, while in Vlasov-Poisson, you regain two derivatives here. So your force, it's one more regular than u, than f, sorry. Here, you have a clear loss of derivative because the force is one derivative less regular than f. It's a gradient of rho. So you see the link, the kinetic equation, you have a loss of derivative, it's singular. And in general, because of this loss of derivative, you may prove it's ill-posed in the cells of Hadamard. Because there are some profile in velocity around which your linearized system may display growing mode and unbounded unstable spectrum. Okay. So you are in poles in general. So if you want to be well posed and in some sense justify the limit at the same time, you have to ask for really precise and really demanding condition, okay, of structure. Okay. So or maybe either you work in the analytic regime. Okay, it's possible. So first result is from Grenier. Yeah, sorry. Yeah.
You have a -1 of the.
Here.
No. Second, left operation, second line.
Here.
Yes.
Yes.
So epsilon equal to 0.
Yes. So you have u equal rho -1, but you take a gradient. So the -1, because you take a gradient.
Okay.
Yeah.
Okay. So yeah.
I agree. The -1, but you will take a gradient.
Right. Okay.
Here you're on the torus, so you have to also, but it's just you don't see it after. Okay. So as I said, you can work in some analytic regime. So the first paper doing this was the one of Grenier here. It has been extended after in many situations or variants. Okay. And what is actually known is that it's possible to prove that this singular Vlasov equation is actually well posed in Sobolev regularity, even if you have a loss of derivative. It has been done mainly so in 1D, in some particular case by Bardos and Bess, and the paper we took our inspiration from is the one from Daniel Anquan and Frédéric Rousset, where they prove that for Penrose stable data, I will explain what it is, you can be well posed in Sobolev regularity. So I will build on Penrose stability condition. So here it's on the torus in X and RD in V. So in green, it's what I call the Penrose condition for our equation. Actually, it's kind of the same for Vlasov-Benet, so you will see. So it's a condition on the initial data. It's a structural condition on the initial data. I say that F initial and rho initial satisfies the condition P if pointwise in X, I have this nasty functional 1 minus this one, which kind of look like Laplace transform equations or Laplace Fourier transform equation. 1 minus this one is non-vanishing. Okay, so don't look too much at the term. It's not really important. What I can tell you is that first, this condition is really well known in plasma physics. Okay, and for instance, it's satisfied, as you've seen, by small data F initial. It satisfies for Maxwellians in velocity, okay? And actually, you may think about this condition be satisfied by any one bump function in 1D, say, and so any radial non-increasing profile in V, okay, will satisfy this criterion, okay? But if you have two bumps of same size, it's not satisfied, okay? It's two strings instability in plasma physics. And what is nice, it's an open condition in the Sobolev regularity, okay? So this condition is really famous because it appears naturally when you look at Vlasov-Poisson on the torus. You linearize around homogeneous equilibrium, and this is a spectral condition for linear stability for Vlasov-Poisson. And it has been used as a condition for which you recover the Landau damping for Vlasov-Poisson by Moe and Villani, for instance, which is nonlinear stability for Vlasov-Poisson. But here, be careful, it's on the initial data. Okay, it's not on the profile around which you look. It's on the initial data. It's different. It's different because here it has been used, so the green part, this condition of Penrose stability, if you assume it on F initial, you may prove local well-posedness of Vlasov-Benet. Okay, so it has been used by Anquan and Rousset in this paper. So the Penrose stability condition, sometimes it's a bit unclear picture. Either you do like large time behavior here for Vlasov-Poisson, which is non-singular, you perturb around Penrose profile, stable Penrose profile, or you look at a singular equation and you have to assume it on the initial data for local well-posedness because it's singular. The reason is because there is a hyperbolic rescaling T over epsilon, X over epsilon, which shifts the large time behavior to the local well posedness one, but for the same condition. It's a formal explanation. And here, I will assume a Penrose stability condition on my initial data, which is the same actually, and it's a bit twisted by, say, the spray part. Okay, but it's the same. So here the theorem. So I insist on this fact. It's for the viscous case, Navier-Stokes case for the fluid. I don't claim anything for the airway case. Okay. So it's a result with Daniel. So you take nice initial data. I don't care about the exponent. The main challenge is to do it for finite regularity, whatever it's big or not. Okay? What is important is that you assume that your initial data satisfies the Penrose condition without vacuum, say. Then you can construct a unique solution on an interval of time 0t, okay, f for u. So u is living in the standard regularity, high regularity space for Navier-Stokes, okay. And here you see, because of the loss of derivative, you still have, it's reminiscent of this loss, you have a shift of one derivative between f and rho. Okay, it's still reminiscent of this. And you can propagate the Penrose condition. Okay, so to my knowledge, this is the first time that this Penrose stability condition appears in this fluid kinetic. You have been able to discover it in some sense in this fluid coupled with particles. So what I've shown you before, so there was collisions. Actually, you can use it, same theorem if you have collisions. And you can also include a non-barotropic fluid. Actually, so you include the temperature of the fluid or the internal energy of the fluid, it works. Yeah. But it's already complicated like this. So the heart of the problem is like this. And it's somehow coherent, I should say maybe, with a preliminary result by Buet, Després, and De Villette, which is a linear stability result for fixed-spray equations around the Penrose profile. So it's a linear stability in L2. Okay, so of course it doesn't give you well posedness at all on a linear problem. It's more an information on the large time behavior, in my opinion. But we kind of identify both in an independent way, actually, this Penrose condition. So it seems coherent with what they have done. Any questions so far? So it's a local well posedness result. So it's a bit maybe boring, but we'd like to present some maybe tools in the proof that may be of interest. I don't know. Okay. So what you do first, you remove the loss of derivative. So you do what you want. Here, we choose to smooth the force field in the Vlasov equation. So I introduce this elliptic regularization. Okay, there is a parameter epsilon which is pretty positive, and then I smooth the gradient of the pressure in the Vlasov equation, and I replace just this term by this one. Same model. Now you don't have a loss of derivative, so for any epsilon strictly positive, you will be able to construct a solution indexed by epsilon on a time interval that depends on epsilon. Okay, you don't solve the problem, and you may expect that when epsilon goes to 0, your time of existence t epsilon shrinks to 0. So you don't prove anything. So what you want to prove is that you want to find a time t independent of epsilon on which you have, for instance, uniform bounds in epsilon that will allow you to pass to the limit on the interval 0t when epsilon goes to 0 by weak compactness. Okay? So what you do a bootstrap on this quantity and epsilon. So for you, I put the, okay, so if you want the functional spaces here are the one from the theorem. Okay. So for you, I put more derivative because it's parabolic regularized, so it's okay. Here, the main point is that I put a shift of one derivative between f and rho. Okay. It's reminiscent of the loss of derivative because by the former estimates, I can control f by rho. So the main quantity, your main enemy, is the one in the middle. You want to control m derivative of rho. Okay. So you look at the equation on rho. So I rewrote the equation on rho, and you see that okay, rho actually doesn't talk to f. It talks to jf and rho f, moments and velocity of f. Okay. So what you will do, if you want to estimate m derivative in this equation, you will have at some point to estimate m derivative of jf and rho f. You will pay. You will apply dm. You have m derivative going on jf on rho f. So now you go back to the Vlasov equation and you try to estimate derivative of moments. I do it, for instance, for rho f. So up to a lot of commutators, and because it depends on x and v also, so it's a bit nasty. You may be able to, so first you take derivatives, then you use kind of Duhamel subtle say formulation, and you use the trajectories that, so without detailing, that allow you to write this decomposition. You may write m derivative of rho f as an integral in time, so it's coming from Duhamel, integrated in velocity, because it's rho f, okay, of your main tangent part, which is a gradient of the force field, which is a gradient of m derivative of rho with the regularization. Okay, this is this part. And it was coming from the Vlasov part, so you have a part here, which is the Nabla-V, f, and you have integrated and used trajectories. So here you are integrated along the free flow, not of the free transport, because, so okay, I come back to the blackboard. So here, the free flow is not dt plus vdx. It's dt plus vdx minus vdv. Okay, so you have a friction term. So here, that's why you have an exponential here. Okay, it's not vdx, it's vdx minus vdv. It's the characteristics for vdx minus vdv. Okay, plus a remainder. So if I call this one an integral operator kg with friction, okay, this is this one. But you may know that in kinetic theory, what you like is transport equation with a free transport. So I will plug by brute force the same operator that I will detail after, but with a free transport here. And of course, I pay the difference. Okay. So I will define this operator just after. But what you want to do is to plug this expression in the equation on rho. But on the equation on rho, you have a divergence. So you expect, or you hope for a better control of this difference, which has to be controlled not in L2, L2, but in L2, H1, because you have an extra derivative here. So if you want the green part to be your main part, the remainder has to be controlled in L2, H1. Because of divergence. So you do it through what I call friction type smoothing estimate. So these are the two integral operators I was mentioning before. You have K free and K friction, depending on the kernel G. You integrate in time, in velocity. Again, you take a gradient along a curve times a kernel. And the curve is either the one from the free transport or either the one of the friction transport. Okay, I hope it's clear, the definitions of these two operators. And you see, this operator in X, well, you take a gradient, right? So it displays an evident loss of derivative in X. But there is this so-called friction type of smoothing estimates lemma, which tells you that actually K free, if G is nice, is a bounded operator in L2 in time, L2 in X, in spite of the gradient here. Okay. And this is coming from the averaging procedure. It's better. So for K3, it has been used and proved by Daniel and Frederic, the paper on Vlasov Bene, say. But here we need more. So we have proven the same for K friction, actually. And you remember, we needed more. We needed L2H1 for the difference. And actually, it's true. The difference, it's even better. You go from L2L2 to L2H1. You are regularizing. So this effect is really in the spirit of averaging lemmas in kinetic theory. So they are used everywhere. The one of the first paper by Goldstein, Bertan, and Santis. But as I said, the averaging lemma will give you a gain of 1/2 derivative, not of a full one. Okay, so it's not covered at all. It's really specific to the structure of this operator. So if you know it, up to a lot of reminders, you are able to decompose m derivative of the moment as a main part, which is this one, K friction, K free, sorry, yeah, applied to m derivative of rho, plus a remainder. And you want to plug this in the equation for the derivative of rho. And you want to track the main part, the main order part. So I come back to rho. You remember, you want to estimate m derivative of rho. Okay, this is your main part in L2. So you look at m derivative of rho, it satisfies up to remainder this equation. Now you have m derivative of the moment. Now I plug the former decomposition using the integral operator, this equality. So you are here, and the green part is what is coming from the former decomposition. So now it's a closed equation on H, which is fine. There is no F now. And now there is a magical computation, maybe believe or not, but it's true. So here, which is nice, that the first operator is just the transfer by U, dt plus U grad. And actually, this operator, you can find it also in this divergence. Because of the averaging procedure here, you have time derivative and so you have time curves and so on. Here, this one, there is a time derivative in this operator. So you can re-express this, and what you can do is you can factorize up to reminders. You can factorize this expression between the transport by U, so super simple. So you have the identity applied to this, and you have this integral operator acting here. So you are able to factorize the equation m derivative of rho between a nice hyperbolic part, transport by U, so you are fine, times kernel operator. So now the aim is kind of clear. You call capital H dth plus U grad H, and you have this integral differential equation. Okay? And you want an L2 estimate in time and space on capital H. So it means that you want to say invert this equation, which is linear in nature. So what is what we can do is that, okay, it seems a bit fancy when you see it for the first time, but the idea is just to rewrite this integral operator, which is a bit nasty, you decompose H in Fourier, and you plug inside, and you rewrite the operator. So up to some conjugation in time, you can relate, actually, this operator to a semi-classical pseudo-differential operator in time and space, not in space, in time and space, which is a bit different from Blazov-Bennett, which has the following symbols. Okay, but it seems a bit strange, but it's just decomposing H in Fourier, plugging this here, and you obtain this operator. Okay? Which is A, so I don't detail, but you see a bit appearing what was in the Penrose condition, actually. Okay, same Laplace Fourier transform. So you have been able to rewrite your integral differential equation on H as a pseudo-differential equation of symbols 1 minus P. And what is P? It's super simple. It's just your Penrose function, which was appearing in my condition P. Okay. So if you like a pseudo differential equation, it's like it's made to be like algebraic. If you want to invert this equation, what you want, up to some complicated theory, you just want this symbol to be non-vanishing. Okay, all the variables. And this symbol to be non-vanishing is precisely the Penrose condition. Okay, 1 minus b must be bounded away from 0, at least initially, but you propagate this condition for short time. If you have this, you can kind of invert up to some commutators by some classical calculus, I'll say, the differential calculus. You have an elliptic operator, you apply the invert, kind of, and you can obtain estimates for h in terms of s. And here, so there is this more subtle detail that you use a large parameter approach, say à la Mathgeo, to close your bootstrap argument in the end, just to absorb the remainder.
Essentially, you construct the parametrics of...
Yes, yes.
Okay, so it's like...
But we do it by hand. But you see here, there is epsilon. Okay? So there is epsilon and gamma. But what is nice is that by homogeneity of the symbol, here, there is something here, you can absorb the epsilon which disappears, because it could be and you have this extra gamma, which appears as a, say, okay, what I know from Mathgeo on boundary layers, it exists, or hyperbolic stuff, it's used. So there is a well-designed calculus for this, but here you can do it by hand. Kind of. And you may be, so you can close an estimate on H in L2, L2, and you are fine. Okay, you can conclude the bootstrap, obtain a solution. Okay, and the uniqueness is kind of obtained with the same technique in something. Okay, so now you can tell me, okay, maybe you have found a class of initial condition for which you are well posed, but what if you are not satisfying the Penrose condition? Okay, so it's a sufficient condition, is necessary. So there is the same issue for this singular Glazov equation in plasma physics. It's the same question. So actually, the main message is that if you are not Penrose stable, if this condition is not satisfied, you are ill-posed. Okay, so it's a kind of necessary and sufficient condition. Fine. So to do this, we look at this particular strategy, say. So you look at a particular profile solution of the Glazov equation. Okay. So I look at f bar 1 and 0. So 1 is for the density, 0 for the fluid, and f bar is this one. So it's a bit more complicated than Glazov-Poisson. For f bar, you have to be time dependent because of. Okay, I come back just to show you. Maybe it's in interest. Because of this minus v, the friction term. So you cannot be just depending on v. You have to depend on time because you have a friction, you have a concentration. So this kind of profile are always solution to the six-point equation. And initially, you say, okay, I ask that this profile, okay, is not Penrose stable. What does this mean? Kind of is that there exists a frequency k and a lambda, which is of real part strictly positive, such that the condition is breaking. So 1 minus this functional blah blah is equal to 0. So it's a dispersion relation, and you have a growing mode, say, for this profile. What you want to say is that at least around this profile, you may be able to find a growing mode with unstable and bounded state. Okay, is this dispersion relation is satisfied? And so this is a theorem, which is not totally finished, but say kind of. So with Émeric Barada in Lyon, in Daniel. So you take an initial data, which is Penrose stable, in that sense. Then you can construct a family of solutions, F delta, Rho delta, U delta, and time T delta, such that you have this convergence. So you measure the distance between this solution and this profile over the same as the initial time. You put a lot of derivative initially for any s, and you just put L2 here, and this quotient is divergent. Okay. And you can do it for any S, any alpha between 0 and 1, and the time for which it's true is converging to 0, the T delta. So what does this mean? It means that even for short times, even if you pay a lot of derivative, your flow map cannot be C alpha for any alpha. Okay? Even if you pay a loss, as you want the loss of derivative between the initial and the solution, and even for short time. So it's a strong ill-posedness result in the sense of Adama. So it kind of follow, say, the technique or the framework built by Daniel and Tuan and Nguyen here, which kind of allows you to go from linear, unbounded, unstable spectrum to the nonlinear case, actually, okay, and to obtain this quantified ill-posedness result. And here you need a lot of regularity on everything, but with Emmerich and Daniel, we are trying to reduce this stuff. What is happening? Okay, for instance, you know, Penrose stable data is, for example, a Gaussian, one bump function. But so a limiting case of this is, in velocity, a direct mass. Okay, so a direct mass is kind of a limit case of a Penrose stable function. You can take now two bump functions, which is unstable. The limiting case is two direct masses. Okay, but this kind of solution are really singular in velocity. Okay? But you may expect, as in the two stream instabilities, the same kind of result. So we are trying to reduce the regularity, what you need for you. So you need another framework. So to conclude, so these two results kind of answer the questions in the case nu equal 1. You are well posed locally in time in subalep spaces if you are Penrose stable at the beginning. If you are not, you are ill. So now there are a lot of questions that may arise from this really preliminary results, in my opinion. So in the case nu equal 1, can you tell me something about global well-posedness at the same time the large time behavior? Okay. So what is known, at least in the thin spray case, the Vlasov-Navier-Stokes name case, is that you expect a convergence towards direct masses in velocity. So the fluid and particles will align their velocity for large time. Okay, you will converge to something. Okay, maybe it's not so clear, but it will. And you will have the friction gaining over this effect, and you will align your velocity. So you will expect, as you have seen previously, monokinetic behavior. Okay, but so it has been proven by Diane Kwana, Iman Moussa, and Ivan Moyano on the thin spray case, and it's kind of used subtle modulated energy approach that formally exists at the level of the fixed spray equations, but okay, it's just a formal computation. And the main part is that here you have a local well-posedness framework for really strong solutions, okay? But you may expect to capture in the large time behavior, really a singular profile, direct mass. So how do you combine this framework of strong solutions with really like weak asymptotic state? Okay. I should mention the fact that you really expect this profile because when you put the Boltzmann type operator, the Vlasov equation, in the kinetic equation that you have to do actually, you expect a loss of energy because the particles, it's not a Biard or stuff, so it's not elastic Boltzmann. It's inelastic Boltzmann operator that you have to use. So you don't conserve the energy, you conserve the mass momentum, but not the energy. And so you don't expect global Maxwellian velocity like for Boltzmann usually. You expect, because of the loss of energy, direct mass. It's like kind of called a cooling effect. And so it's coherent with this direct mass infinite. So maybe the use of the collision operator will help you, but natural questions. that Laurent Davidet is asking for. Okay. What about the Euler case? So as you have seen before, U for me was kind of a parameter. U is regular. I can use it, but I don't say anything on him. It's always better. Here, if you consider Euler, it's really a part of a problem. So it means that kind of before, when you were considering this, I was plugging F in the equation on rho. Here you have to do the same, but also on the equation on U. So you have to find kind of a way of inverting this, but for a system on rho and U. And you see here, it's really based on algebraic miracle. So on the system, as long as you don't find it, it's okay. You may expect something, but maybe not. Okay. And last one. So coming back to this Boltzmann operator case, actually, since you are in the fixed spray, it's even worse than the derivation for Boltzmann. You are not in the Boltzmann grad case. So you expect actually highly dominant collisions. So you should always put a 1 over epsilon in front of the collision operator. And this is this hydrodynamic limit when epsilon goes to 0, which provides the derivation at this formula of two phase flow equations, okay, between fluid and gas. And this hydrodynamic limit, at least even for short times, we don't know because, okay, inelastic Boltzmann, it's a mess on itself. So here you combine it with not so easy stuff. So it's also an open question. And okay, I think I will stop here. Thank you very much.
Thank you, Lucas. Are there any questions?
Out of curiosity, this Penrose, is it the Roger Penrose or the Oliver?
No, it's
Penrose?
Oliver Penrose, since it's a cousin of
Brother.
brother or cousin. Okay, I don't know because there was another one. I think.
Sorry?
I think there is another one. No.
I think there's a third one, but Oliver is the brother.
Ah, it's brother. Okay. Yeah.
Maybe I have a question. So about these questions of lifetime behavior and global closeness. So you're thinking this in sort of close to equilibrium type results, or
Yeah.
more
So yes, so it's not okay. So it's not easy because you cannot linearize the equation because you cannot linearize around the direct mass. So in this approach from for the thin spray, it's based on the fact that initially an modulated energy is small. It kind of means you are close to a direct mass, but it's at the kinetic level, so it's not so easy to say. It's not a linearization procedure. It's more complicated. It's really different from Weber-Poisson when you can write the linearized equation and so on. Here you cannot.
Right.
So what you are doing actually is to kind of develop a framework when you can, it's a multi-phase flow framework, when you can rewrite Vlasov equations as a superposition of an infinite amount of conservation laws, which is a pressureless Euler flows. And in this framework, you can see the direct mass if you want. And here you can linearize, but actually we are doing this now with Enrique and Daniel for the thin spray first. So redoing these results, but in a different setting when you linearize. And in this case, if you write this simplified approximation, you linearize and there is a kind of spectral gap which appears, which you don't see at all here. It's a totally different approach. And so maybe it's possible, but it has to be combined with everything here for the fixed spray. So yeah, it could be a possibility. But yeah, it's close to. Here, for the thin spray, if you want, the stable manifold is all the direct mass. So you start close to a direct mass, and it's like in Euler, you will converge to another. But close.
Yeah.
It's really the same. But the whole manifold, which is stable, is all the direct mass at a constant velocity. Because you're on the torus, so you expect that U tends to a constant, and the velocity for the particles to the same constant.
Okay. Yes.
Can you remind who proposed the model? What was the equation?
Yeah, it's
What was the
It's
name?
mainly O'Rourke. It's first Williams actually and O'Rourke. But, so these are guys from Los Alamos in the USA, which were working on what you can imagine in the desert, right?
I was just curious.
If you have seen Oppenheimer, then you know.
No, it was curiosity.
Yeah.
I didn't know.
Yeah, it's super hard to find the paper, and in France, there is a CEA, Commissariat à l'énergie atomique, which are really using this, but you cannot find the code because it's classified.
In fact, I was curious because I've been doing the multi-phase fluid dynamics for like the last 15 years, and I have never seen it. So you can never learn. You can always learn new stuff.
I think it was meant to be related to these two-phase flow equations, which are macroscopic, that have been developed. I guess you see this this alpha nabla p. It's reminiscent of this common pressure. So for one flow, it's alpha nabla p, and for the other one, it's 1 minus alpha nabla p. It's really the same. It's really meant to be. When you do the hydrodynamic derivation, you obtain this formula.
Okay. If there are no more questions, we can thank Lucas again. And we come back at
Comunque penso di sì, che abbiamo
No, ci sono, sì, abbiamo mandato tutto lì, abbiamo mandato. Quindi cioè, lì anche sono 80 persone arrivate, però anche gli amministrativi tutti hanno il nostro. Io devo mandare la lista completa, quindi perché si sappia. Più collaboratori, no, sono più, sono 100.
Acceso adesso quindi l'audio.
Adesso l'audio in questo momento è acceso.
Possiamo vedere?
Ci vuoi
No,
vedere?
no, se c'è gente, qualcuno.
Vuoi vedere?
Possiamo iniziare se c'è. Due. Prima erano 4.
Ma uno ero io.
Ah, ok.
E uno eri te, forse.
Non lo so, perché se tu ti connetti conta anche te quando vedi?
Sì.
Ah, ok, allora.
Se mi connetto con YouTube.
Sì.
Sì.
Ah, ok.
Certo, conto che sia. Io direi sì, ho cominciato.
Okay, so maybe we can start the presentation. So it's a pleasure to have Sabino from IMATI, who is also an ECNR, the Sustainable Presentation National Institute in Pavia. And she will talk about vanishing disposable solution for conservation law.
Okay, so first of all, I'd like to thank Roberta and Michele for the kind invitation and for organizing such a nice workshop. Also, I will report on joint work with Fabio Ancona and Andrea Marstone. So, concerning the title, I know it very much sounds like abstract nonsense, but I will spend the first part of my talk explaining basically every single word. So, okay, so let's start with conservation laws. So I will talk about system of conservation laws, namely equation like the purple one written on the slide. So here x is the space variable, and I will always restrict to the case where x is a scalar, so belongs to, for the time being, to R. The equation is a system, so U belongs to Rn, where n is can be greater than 1, and f is a given flux function, which is as regular as we need. And several interesting equations can be written in this form. For instance, the equations of fluid dynamics, like the Euler equations and the implicit magneto-hydrodynamic equations. Okay, keeping in mind something, in this talk, when I talk about Euler, I always mean compressible Euler, so no divergence concentration. And there are also applications to traffic models. So in the following, what I will do is I will basically use the compressible Euler and the implicit MHD equation as a fil rouge, as a guiding example. But my goal, I mean, our goal was to provide a theorem, provide results that applies to general system of conservation laws. How general? Basically as general as we can. So for the time being, I will focus on the Cauchy problem. So I will couple the purple equation with an initial datum, U0. So what are the main challenges in studying this Cauchy problem? So first of all, the finite time breakdown of classical solutions. So think to the Burger's equation, even if the initial datum is very regular, your solution can become discontinuous in finite time. Which means that if you want to look for global in-time solutions, you cannot work with classical solutions. You have to work with, say, distributional solutions. The drawback of the notion of distributional solution is the lack of uniqueness. In general, a Cauchy problem has infinitely many distributional solutions. So to restore uniqueness, what people usually do is they couple the equation with some admissibility criteria, which are often motivated by physical considerations. So, for instance, one speaks about the entropy admissibility criterion, which loosely speaking means that the solution is consistent with the second principle of thermodynamics. Now, I don't want to get into the technical details, what I like to you to keep in mind is that in the framework I will consider, there is a well-established notion of admissible solution, although I'm not going to define it. Okay. Now, what are the main existence and uniqueness results for the Cauchy problem? Well, if I have a single equation, so U is n is the dimension of the codomain. If n is equal to 1, the problem of existence and uniqueness was basically settled in the 70s by Kruskov, who established existence and uniqueness of entropy admissible solutions. In the case of system, in the same of system, well, the story is more complicated. So the existence of an admissible solution was proved in the 60s by Glim. The uniqueness was an open problem for a long time, and it was established in a series of papers in the 90s by Bressan and several collaborators. The Bressan result relies on the introduction of what is called wavefront tracking algorithm, which is a kind of approximation algorithm. And I'd like you to keep this name in mind because it will appear in the following. Another important remark is that the Glim and Bressan theory is based on the assumption that the total variation of the initial datum is sufficiently small. This, of course, is a very restrictive assumption. There's no way to deny this, but it's needed if you want to deal with general systems, because there are counterexamples that show that if the initial datum has finite but large total variation, then the solution may blow up in finite time. So in the following, as I said, I want to establish a theory which applies to general system of conservation laws as general as possible. So I will restrict to small total variation regimes. This, of course, is a restriction, but it's somehow the price you have to pay for generality. And anyhow, I mean, in some cases, also these very specific regimes provide information, valuable information on the general case. Okay. Okay, now another word that I have to explain that appears in the title is vanishing viscosity. So vanishing viscosity is basically the following. So here I have my system of conservation laws, say the Euler equations. Then what I can do is I can perturb it with a second order term. And for the time being, let's consider a perturbation in the form of a Laplacian, which in one space dimension is just a second derivative. I put a small parameter epsilon in front of it. As epsilon varies, I have a family of solutions. And then, as always, I let epsilon go to 0. In 2005, okay, Stefano and Alberto Prestana, by the way, I think Stefano was at SIAC at the time, prove that when epsilon goes to 0, U epsilon converges to the admissible solution of the conservation law. So when it appeared, this result was kind of a breakthrough, but it has a major drawback, which is the following. It does not apply to the physical case. What I mean is the following. So let's consider our system of conservation laws, say the Euler equations. So from, okay, the Euler equations model the motion of particles in this fluid. So from the physical viewpoint, what you would like to do, and I'm saying something very trivial, what you would like to do is you would like to approximate it by using the Navier-Stokes equation, so the equations for a viscous fluid. Now, the Navier-Stokes equation in one space variable can be written in this form, where D is a matrix. So it can be written in this form, where D is a matrix. Now, if D were the identity, then this purple term would boil down to this blue term. But for instance, in the case of the Navier-Stokes equation, this is not the identity. What is more, and what is more, and what makes the problem more complicated from the technical viewpoint is that D is not even invertible, it's singular. Its rank is smaller than n. And to see this is fairly easy because, well, I said that we have the compressible Euler, so the compressible Navier-Stokes equation, which means that somewhere you have to express mass conservation. So the mass conservation is this equation, where rho is the fluid density and v is the fluid velocity. I know you are very much familiar with this. Now rho is one of the components of this bold U, which means that D must have a line which is entirely made by zeros, and which means that D's cannot be invertible. Basically, the same happens for the implicit MHD equation. What you want to do from the physical viewpoint is to take as an approximation the viscous MHD equation. And again, you have an equation in this form where, however, D is not singular, so D is not the identity. It's not even invertible, again, because you have mass conservation. And in the case of the MHD, you can also have more complicated behavior. So the Bianchini and Bressan proof does not apply to this physical case, so the physical vanishing viscosity. As a matter of fact, establishing the result for the convergence in for this class of equations is still an open problem. Okay, so this is bad. So the fact that, yes. Sorry.
Do we know the rate that this converges in the network?
Yes, we know. Yes, it's no.
How does this compare to the network result, which is the consumption of one?
Sorry, to the
result of Kuznetsov? It gives.
Kuznetsov. That's no. Okay, that's for yes, that's for the, for instance, if you have a numerical scheme. I don't know. Okay, I know there's a rate of convergence. Honestly, I don't remember how they prove it. I don't think, because that one applies to, sorry, that one applies to the scalar case. Now here we have a system. So, yeah. So if I'm not wrong with Kuznetsov, you basically use Kuznetsov doubling of variables, and then no, you cannot use that one. But because you don't, because it's a system. But I think it's a known, the rate of convergence right now. I don't remember, but it's
the rate of convergence is
square root of epsilon. It's like the, okay. Yes, it's like for the scalar. Yeah. As I said, okay, so this establishing the convergence in this case is an open problem. Okay, this is bad, of course, because it's a very natural problem we cannot solve. But from the point of view of the conservation law, it is bad as not, but not as bad in the following sense. We don't know whether, so let me call purple U epsilon the solution of this equation. Now, we don't know whether U epsilon converges or not, but what we can do is basically we can do the following. We assume that it converges, then it's fairly easy to see that it converges to the admissible solution of the conservation law, which means in particular that it converges to the same solution as this so-called artificial viscosity. So this U epsilon is the solution of this system, which is the one considered by Bianchini and Bressan. So to sum up, what you have for the Cauchy problem is that for a large class of viscous approximation, you know that if you can prove convergence, then what you select in the limit what you recover in the limit is the admissible solution of the conservation law. In particular, the limit does not depend on D, which is somehow reasonable because, well, in the limit you don't have D. Here you have 0. Okay, one of the typical, relevant features of the initial boundary value problem is that for the initial boundary value problem, if you take the very same viscous approximation, the limit depends on the viscous mechanism. What I mean is the following. So to focus on the main point, let's consider a toy model. So I take the linear case. So I take this equation. A and D now are constant matrices. And for simplicity, let's assume that A is symmetric and invertible and D is positive definite. So the simplest setting I can think of. I consider the initial boundary value problem. So x belongs to 0 plus infinity, x is equal to 0 is my boundary. It's one space dimension. Then I assign an initial and a boundary datum. And for simplicity, I assume that they are constant. So very easy. Okay, now what happens in the limit? In this case, you can prove convergence. In the limit, you have the following. You have that the solution is the limit is a solution of the linear hyperbolic equation, of the linear equation. The solution has this shape. It's self-similar, so it's constant along lines that start at the origin. It is piecewise constant and has discontinuities along finitely many blue lines. And it attains a boundary value that I called U bar. Now, what is important to keep in mind is that in general, U bar is not UB. So you have a loss of boundary, you have a different boundary condition. In the limit, you recover a different boundary condition than the boundary condition you impose on the parabolic equation. What is the relation between UB and U bar? The relation is that there is a boundary layer, which is in this one-dimensional setting is just a function W, which is up to a change of variables, a steady solution of this equation, so a solution that does not depend on time, and which attains the value, which attains the value UB at 0 and converges to plus infinity, to U bar as Y goes to plus infinity. Now, in this simple case, you can write basically an explicit formula for that U bar has to satisfy. I mean, I'm not interested in this explicit formula. What I'd like to stress is that this system depends on D. The fact that UB and U bar can be connected by a boundary layer depends on D, because this equation depends on D. Which means that U bar depends on D, which means U bar is the boundary datum attained by the solution, which means that the solution depends. And I mean, depends in a dramatic way. When you change D, more often than not, the solution changes. And this is something that you cannot avoid. I mean, it's a typical feature of the initial boundary value problem. Okay, now I'd like to get a bit to the point and try to explain what our goal in the paper was. And what I will do is I will first explain it in a very hand-waving way, and then I will go back to this point and be more precise. So let's consider the initial boundary value problem. So my space variable belongs to 0 plus infinity, x is equal to 0 is the boundary. What we want to do is we want to construct a global in time admissible solution of the conservation law, which is consistent with a given viscous approximation. Where I assign the viscosity and the boundary datum. So for instance, if here I have the Euler equations, here what I want to take are the Navier-Stokes equations. If here I have the inviscid MHD equation, here what I want to do is I want to take the viscous MHD equation. And again, constructing the solutions of the, say, Euler equation by taking into account the underlying viscous mechanism is something that is interesting, because if you want to select the physically admissible solution of the Euler equation, you have to pick exactly the right approximation procedure here. You cannot take you cannot take the artificial viscosity. You really have to take the Navier-Stokes equations. Now,
excuse me.
Yes.
We are in 1D order.
Yes. 1D.
Yeah, but what are the final results about regularity without a boundary? No, I don't remember. That's a delicate question anyway, because Euler.
On Euler.
Okay, no, okay, that's classical. Okay. You have BV for small data.
Yeah, I mean small total variation regimes.
Okay. No, sorry. The question Navier-Stokes for 1D without boundary.
Without boundary, there is like I actually don't need the results, but you can use, for instance, Kawashima.
Okay.
These are standards.
I remember there are some.
No, maybe there is something more updated.
Results in 10 years ago, maybe.
I'm not aware, but
because that's since it is not classical viscosity.
No, sure.
But
I mean, Kawashima Shizuta applies to general mixed hyperbolic parabolic systems.
But even without boundary, you are not in the framework of the equilibrium sum.
No.
Even
no. I mean, even if for the if you don't have a boundary, even if for in the case of the Cauchy problem, the convergence of this approximation is an open.
Okay.
It's open. Okay, but you can try to characterize the limit. That's what we are trying to do. We don't know whether it converges, but we construct a solution which is consistent with the. Of course, it would be better to be able to go prove the convergence, but we cannot.
Initial data is enough, right?
Yes, most probably yes.
No, I was speaking about the infinity, something like that.
No.
No, there are some results of existence for Navier-Stokes in 1D with partial regularity and some variable and so on. In an infinity, something like that. Not better than that. Sorry.
No problem. Okay, let me say something. Okay, this is technical, but I have to tell you because otherwise I would be cheating. Technically speaking, this initial boundary value problem is in general overdetermined, and the reason is the following: we again have the continuity equation. So we have an equation like this. Now assume that V is, say, negative. Then the characteristic lines of your system are exiting the domain, which means that you cannot impose a boundary datum on rho if V is negative. Now here, keep in mind that rho is one of the components of U, which means that here what I'm doing is instead I'm exactly imposing a boundary condition on rho. And in this way, I'm overdetermining the problem. Now, this is a technical problem. It can be solved by introducing a proper formulation of the boundary condition, which, however, is, it makes the notation more complicated. So what I will do in the following is I will basically cheat. So I will pretend that this condition is well posed. although in general it's not. And okay, please believe me, everything I will say extends to the general case at the price of higher technicality. Now, okay, what now I have to explain this word, consistent. Okay, what do I mean by consistent? I will first say something that is correct 90% of the times, and then I will correct myself later on. But I think in this way it's easier to understand. Okay, so keep in mind that here, for the time being, I'm not assigning a boundary condition on the conservation law, so on the, say, Euler equation. So what I will require, and this is my consistency condition, is that for almost every t, there is a boundary layer, which is again a steady solution of the viscous equation up to a change of variable, which connects, so W0 is UBT, the datum imposed on the parabolic approximation, and which converges to plus infinity to ut0, where u is the solution of this equation. So it's the hyperbolic trace. Now, again, this consistency condition depends on d, as it should, because this system depends on d. It's an ordinary differential equation that depends on d. So
the solution depends on t anyway. Because your
it should be WT, but I didn't want to.
Just a parameter.
Yes, it's a parameter. So for almost every t, you have to find a boundary layer which depends on t, such that this is false. Okay, this is almost my consistency condition. Okay, actually it's not. Things are slightly more complicated, and the reason why they are more complicated is because I want to consider the characteristic boundary. So now I'm explaining, I think, the last word in the title. So let me give you some definitions. So we have a system of conservation laws. So the system is strictly hyperbolic if the following holds. You take the Jacobian matrix of the flux, GFU is a matrix. You compute the eigenvalues. Well, strict hyperbolicity dictates that the eigenvalues are real and distinct. So you have n real eigenvalues that you can order in this way. Now, assume that you are on an initial boundary value problem, and again, my domain is 0 plus infinity, the boundary is x is equal to 0. The boundary is characteristic if one eigenvalue can attain the value 0. In other words, the boundary is not characteristic if all the eigenvalues are bounded away from 0, either strictly positive or strictly negative. If you have a characteristic boundary, this means that you can have, say, shocks or concave discontinuity or rarefaction waves that are almost or exactly parallel to the boundary. In particular, you can you have to take into account the possibility that you have a zero speed shock or concave discontinuity that sits exactly at the domain boundary. Okay, keep in mind this. Now, one might think that the boundary characteristic case is just a figment of my imagination. It's not. It's something that you can have. For instance, the Euler equations in 1D are a system of 3 equations. The second characteristic, second eigenvalue of the Jacobian matrix is v, the fluid velocity. The invested MHD equations are a system of 7 equations. The fourth eigenvalue is again v. V is the fluid velocity, and there's, I mean, in general, it can attain the value 0. I mean, it's a legitimate value. And if v is 0 or close to 0, the boundaries characteristic for the Euler equations and implicit MHD equation. This is just an example. Okay, now I can give you the exact formulation of the consistency condition that I'm gonna consider. So we have our system of conservation laws, Euler equation, implicit MHD equation, have a viscous approximation, Navier-Stokes viscous MHD. I assign a boundary datum here, UB. The consistency condition is this relation here. So for almost every t, the boundary datum of the conservation law has this d relation with the parabolic datum. And the d relation is the following. So we say that U bar and UB are in this relation. So U bar has this d relation with UB. U bar and UB are data in Rn. If the following holds, there is a third state, U underscore, such that, okay, f of U underscore is equal to FU bar. And these are the Rankine-Gogno conditions for a zero-speed shock or contact discontinuity. If you have a shock, then you also require that the shock with U bar on the right and U underscore on the left is lax admissible. If you have a contact discontinuity, everything is lax admissible, so there's no problem. And then what you require is that there is a boundary layer, so a steady solution of this equation up to a change of variables, such that W0 is equal to UB, and the limit for y that goes to plus infinity of Wy is U underscore. So in other words, what you are requiring is that for almost every t, the following holds. There's your trace, your hyperbolic trace. There's U bar is your hyperbolic trace. There is a state U underscore such that here there is a zero-speed shock or contact discontinuity, and then there is a boundary layer that connects UB with U underscore. So that's the compatibility consistency condition that I impose. And keep in mind that here I mean this relation depends on D because again this equation depends on D, and hence the whole condition depends on D. Okay, so I can eventually finally give you the our main result. So consider the viscous perturbation of a system of conservation laws, the Navier-Stokes equations, the viscous MHD equations, and let's assign a boundary datum UB. What you have is that under suitable assumptions on F and D, I will specify the following, these assumptions. There is a sufficiently small constant delta such that if the total variation of the initial datum, U0, if the total variation of the boundary datum you impose on the parabolic approximation are sufficiently small, and if this jump is sufficiently small, so the jump at the origin is sufficiently small, then there is a global in time admissible solution of your system of conservation laws, which is consistent with the given viscous approximation. Okay, so this is our result. And okay, of course, we work in, as I said, we work in small total variation regimes. Okay, a couple of remarks. To prove this result, we introduce a new wavefront tracking algorithm. This is a boon per se in the sense that wavefront tracking algorithms are a quite flexible tool. In particular, they have been used by Brestan and collaborators to establish their uniqueness results. And it can also be used to establish fine properties of the solution in terms of very weak regularity. We are fairly confident that our techniques could be applied to establish uniqueness of this solution. However, well, basically the paper was 70 pages long, so we decided that we could leave the uniqueness for future work. So for the time being, it's just an existence result. Okay, now let me give you some references on the, I will give you very few references. I apologize. I mean, it's a very incomplete list of references, and I would be unfair to a lot of people. We apologize for that. Let me, I will give you some references concerning existence results for the initial boundary value problem for a system of conservation laws in one space dimension. So I have my system of conservation law, my domain, x is equal to 0 is the domain boundary. I assign initial datum and I assign a boundary condition. I'm not giving you the exact formulation of the boundary condition because it's different. It's different in the works, the different works that I'm gonna quote in the following. But let's say you assign a boundary condition. Okay. There are fairly old results by Goodman and Monique Sablet-Pichon who establish existence in the non-characteristic boundary case. So all the gain values bounded away from 0. The Navier-Stokes, the fluid velocity is bounded away from 0. Then there is a result which is maybe the closest result to our work, which is due to Deborah Amadori. Now, Deborah introduced a waveform tracking algorithm, different from our algorithm, which allows to handle the characteristic boundary case. From the point of view of the results, the main difference between our results and Deborah's result is that we use a different formulation of the boundary condition. So she used a condition that was introduced by Dubois and Leclerc. And in the boundary characteristic case, this boundary condition is different from our condition, which means, and it's different in the sense that we get different solutions. I mean, the solution that Deborah constructed is different from the solution we constructed. And the novelty and the gain of our analysis is that, as I said, our solution is consistent with the viscous approximation. Okay, let me also quote that there is a result by Fabiancone and Stefano Bianchini that provided a very complete analysis. As a byproduct, this analysis provides basically the proof of our theorem, but in the case of the artificial viscosity. So in the case, the viscosity is given by this second order derivative. Okay, so to wrap up, the main novelty of our work is that it's the first case where we have existence results for initial boundary value problem that explicitly take into account the underlying physical approximation. And in the boundary characteristic case, to the best of my knowledge, this is the first general existence result that is consistent with the physical viscosity approximation. Okay, now let me say something about the assumptions we impose on F and D. So, as I said, on the system of conservation laws, we assume that the system is strictly hyperbolic, so real and distinct eigenvalues. we assume that every vector field is either generally nonlinear or linearly degenerate. I'm not gonna define these words because they're fairly technical. They are very standard assumptions that you had, for instance, in the papers by the exam and also by Lee. Okay, now what we assume is that we have a bunch of conditions that were basically introduced by Kawashima and Shizuka. I think Roberto is very much familiar with that. But I'm not gonna give you the exact condition, but they are very fairly standard assumptions in this class of problems. So they are fairly standard assumptions for mixed hyperbolic parabolic systems. And then we have other assumptions that have been introduced in previous works with Stefano Bianchini, and that are used to handle the system of the boundary layers. Basically, to write in a treatable form the system of boundary layers, so the system of steady solutions of these equations. Again, I'm not going to give you the technical details. What I'd like to stress is that all our assumptions are satisfied by both the Navier-Stokes and the viscous MHD equations, written in both Eulerian and Lagrangian formulation. And if you're familiar with the MHD equations, we can cover both cases of null and strictly positive magnetic resistivity, which I mean, the fact that it's null when the magnetic resistivity vanishes, the rank of this matrix changes. Okay, just as the last slide, let me tell you two things about the main technical novelties. The paper is long and technical. In my opinion, two are the most interesting point from the technical viewpoint. The first one is something that in the jargon of wavefront tracking approximation are called the interaction estimates at the boundary for the characteristic field, which means the following. Suppose that I have a contact discontinuity or a shock or a rarefaction wave with speed very close to zero, and suppose that this hits the boundary, that then in our proof, we have to provide a very precise estimate on the total variation of the solution after this time T star where the shock hits the boundary. And the other point that I think is somehow interesting is that we have to provide, also to show that the boundary condition is attained, we have to provide a very precise analysis of the behavior of the solution at the boundary. And in doing this, we establish some corollaries which provide fine properties of the solution of the boundary, which I think are of somehow the independent interest. And with this, I conclude, and thank you very much for your attention.
Any questions?
So the uniqueness you would say you would probably have it. So for its epsilon, you will have a
No. For epsilon, no. I mean uniqueness. Sorry. Okay, can you? Sorry. Okay. I mean the uniqueness of this system.
Yeah.
Okay, so epsilon disappears. Okay, it's a uniqueness of the conservation law.
Yeah, but,
the solution of it's a unique solution of the conservation law that satisfies this boundary. I mean the epsilon. For this, yes, for every d given d, you have a uniqueness solution. When d varies, you have a different solution in general. I didn't prove it. I expect it to be true.
Yeah, so not the familiar with the MCD in the case where you have physical dispositive. So it's the question. So it's the thick one, the usual one. So you have dispositive.
Well, it depends. Okay, if it depends on this magnetic resistivity.
Okay.
So basically, if I'm not wrong, if so, the magnetic resistivity is positive, the rank is fixed.
Mm-hmm.
If it's 0, it's 4. If I'm not wrong.
Okay, so yeah. And there are more.
I mean, for sure it decreases. I think it decreases to 4. Correct me if I'm wrong.
And it's more or less the same in respect to Mathgeo, so it's more complicated.
Okay, for our analysis, it doesn't change much. I mean, in general, it's very much different. In this framework, we can treat it. We can treat it basically with the same technique.
I mean, you prove by wavefront tracking argument, so
yes.
You have no idea what the real behavior of the Navier-Stokes solution.
No, but you.
It's just formal. I mean, you derive from the Navier-Stokes the admissible condition.
Yes.
And on this condition, you prove existence. So you have nothing about the convergence.
No, we don't have anything.
But why is it so difficult to prove the convergence of viscosity solution? I mean, in the sense that why, I don't know, is it the center manifold difficult to be?
No, it's not the center manifold. It's, I mean, okay. If you want, I can take the Bianchini and Bressan paper and tell you exactly the estimate.
Okay.
Work, but I don't think it's that much. It's, I mean, it's an estimate connected by the center manifold. It's not exactly the center. You can construct the center manifold. If I can give you a very heuristic idea, the idea is the following. So the point is that when you use the center manifold, you basically somehow you diagonalize the system along not along the eigenvectors, but along something that is connected to the eigenvector. And if you here you have the identity,
okay,
this does not create much problems. If you have something more complicated, you have basically that the geometric structure of D does not go along with the diagonalization. And so you have some estimates that do not work.
So you're not sure you have a full family of eigenfunctions for the, the problem, to project the problem on.
No. We construct the center manifold. It's not a problem of the construction of the center manifold. It's really a problem of the estimate.
Okay.
I mean, there are some estimates that depend on how these the vectors they use, the R tildes they use, go along with the viscosity. And this, I mean, you have when the you have the identity that's something that vanishes, and when it's not the identity, it does not vanish.
I mean, the problem is the degeneracy or the fact that D is not the identity, not diagonal.
Okay, I think it's open even for the case. Okay. It's basically open even if in the case of when it's not the diagonal. There's a perturbation. I'm aware of some perturbation results, so very close to the diagonal, but not exactly the diagonal. As far as I know, it's open even if it's constant and not diagonal.
Okay. A and B. I mean, you have two constants in front of
D. D is constant.
I mean, D is just A rho XX and B U XX. I mean,
okay, maybe you can play some tricks in the specific case, but in general, I mean, if you want to take the Bianchini-Bressan proof, it does not work.
Okay.
For constants, but not diagonal. For sure, the fact that you have a mixed hyperbolic parabolic system is much harder.
And physically, for Navier-Stokes, you have conservation of mass without diffusion, so it is
Sure.
meaningless to put
Sure.
an artificial viscosity on the first equation.
Yes, sure. And in the case of, as I said, in the case of initial boundary wheel problem, the problem is that with artificial viscosity, you get the wrong solution.
Yeah.
Is there any, I don't know, even partial results in higher dimension? I mean, which is
No.
the usual question.
There is no,
Never,
there
right?
is no uniqueness. There is no uniqueness.
No uniqueness.
No, for Euler for compressible Euler in more than two space dimensions, you don't have it.
Uniqueness, yes. And also,
No, you can. Okay, there are something that is so the all existence and uniqueness results that I'm aware of. I mean, in this framework is for an artificial, with a system with modest physical meaning, which is the so-called Kiffitz and Kranzer system. And there you play a trick because basically the system decouples in a scalar conservation law plus a transport equation where the coefficients depends on the solution of the conservation law. And then you can apply the Ambrosio-Bernard-Young's theory. And okay, it's not trivial, but you can prove existence. But yeah, but I mean, the general case is hopeless, or at least we don't know.
Okay, so if not, let's
Thank you very much.
now there are break and we come back at 4. Claudio, vuoi fare?
Sì, perché